We are now going to move on to a discussion of capacitors, but before I introduce capacitors, I first want to devote a slide to talking about batteries. A battery is a type of circuit element that we will encounter often in this course, so we should formalize what do we mean when we say battery. For the purpose of this course, we will say that a battery could be thought of as any device that maintains a constant electric potential difference across its terminals. A battery contains two terminals, the positive terminal and the negative terminal, and often I'll refer to these as the plus side and the minus side of the battery. Shown here is a circuit symbol for a battery. The circuit symbol consists of alternating short and long lines, and the side of the circuit symbol that ends in a long line is the positive terminal side of the battery. The side of the circuit symbol that ends in a short line is the negative terminal side of the battery. When I say a battery is a device that maintains a constant potential difference between its terminals, that means that no matter what happens, there will always be the same potential difference between these two ends of the battery. If I hand you a 9-volt battery, there will always be 9 volts between the plus side and the minus side of that battery. You could plug that battery into an incredibly elaborate circuit. You could have really interesting things happening in that circuit. But no matter what happens in your circuit, there will always be a 9-volt potential difference between the plus side and the minus side of that 9-volt battery. Batteries work by producing an electromotive force, an EMF, and this is often symbolized with a cursive E. The EMF pushes charges around through a circuit in a certain direction. An analogy to batteries and EMFs can be made with water pumps and water pressure. A water pump is a type of device that produces a water pressure, and that water pressure causes water molecules to flow around through a system of pipes. A battery is a type of device that produces an electromotive force, and that EMF causes charged particles to flow around through wires in a circuit. Even though the word force is used in electromotive force, EMF itself is not a type of force. In other words, EMF is not a quantity that is measured in newtons. EMF is a quantity that is measured in volts. You will often see the EMF of a battery and the voltage of a battery written. For the purpose of what we do in this course, I will say that it is all right to think of EMF of a battery and voltage of a battery as interchangeable ideas. However, if you are curious, there is a subtle difference between these two concepts. If I hand you a 5-volt battery, you could look at the battery, you will see 5 volts written on the side of the battery, so you will believe that is a 5-volt battery. But then if you were to take a multimeter and measure the voltage between the two terminals of that battery, you might get a number that is slightly different from 5 volts. You might get 4.82 volts. Now, why would this be? In the real world, there will be a slight internal resistance within a battery, so that will tend to decrease the voltage of a battery by a little bit. Also, batteries tend to degrade over time, and the voltage between the two terminals of the battery will tend to be less than what is printed on the side of the battery. So the ideal case is not always going to match the real world case. However, for the purpose of solving circuit problems, if you could solve a circuit problem with a 5-volt battery, you could solve a circuit problem with a 4.82 volt battery. You're just making your math a little more complicated. To motivate the idea of capacitors, let's consider a scenario where we have a battery that has a wire connected to either terminal of our battery. So we're going to consider this picture. Based on the orientation of this battery, I expect that the battery will push charges around through the wire in a clockwise direction. So I could say there will be a current that is flowing clockwise through the circuit. We did not formally introduce electric current yet in this course. For today, just know that electric current is a movement of charges. Electric current is designated with the symbol I. Now, if I were to cut the wire right there, what do you expect to happen to the electric current? The battery is trying to push the charges through the wire in a clockwise manner, but when the charges end up right here where the wire was cut, they will not be able to travel to the other side of the wire. Since the charges can no longer move, the current will stop flowing. At the location where we cut the wire, let us place two large conducting plates. So let's suppose we have two large metal plates, and we're going to place those two plates on either side of the wire where we cut it. So we're going to have a picture that looks something like this. Here is a side view of the two plates connected to the wire, and here's a view with a bit of perspective. These plates will be assumed to be parallel with each other, and they're going to be very close together, so that the side length of the plates is much longer than the distance between the plates. And importantly, the two plates are not in contact with each other. There is just empty space between the two plates. We are going to ask the question, what do we expect to happen as soon as we place these two plates into our circuit? We are investigating a parallel plate capacitor that's connected to a battery. When we work with a parallel plate capacitor, we assume that the distance between the two parallel plates is much smaller than the side length of the plates themselves. So the picture I drew on the board here is not an accurate representation of a parallel plate capacitor. A more accurate representation would look something like this, where the two plates are very close together and their distance apart is much smaller than their side length. However, in this example, I am going to need to draw between the plates of this capacitor, so I did need to exaggerate my figure. Because this capacitor is connected to a battery, charges will accumulate on the two plates. Therefore, there will exist an electric field between the plates of this capacitor. You could imagine that if you were standing between the plates of the capacitor, anywhere not near the edge of the plates, these two plates would both, to a very good approximation, resemble two infinitely large sheets of charge. So I could say that the electric field between the plates of the capacitor should resemble the electric field produced by two infinitely large sheets of charge. Therefore, the electric field will be uniform everywhere between the plates. So I could draw the electric field pointing away from the positive plate and towards the negative plate to look something like this. The strength of the electric field created by an infinitely large sheet of charge can be written as sigma over 2 epsilon naught. It is possible to use Gauss's law to prove this. Sigma is the surface charge density of your infinitely large sheet. Because each of these plates, to a very good approximation, resemble an infinitely large sheet, we could say that sigma would be the total amount of charge on one of the plates divided by the surface area of one of the plates. Sigma asks how many coulombs do you have per square meter on your sheet. So therefore I could write sigma as being equal to Q over A. Now, because we have two plates that resemble infinitely large sheets of charge, each having the same total amount of charge and total area, I could write the strength of the electric field as being equal to 2 times sigma over 2 epsilon naught. The direction of the electric field created by the positively charged plate will point away, which, if you're standing between the plates, means downward. The direction of the electric field due to the negatively charged plate will point towards the plate, which again, if you're standing between the plates, will also point downward. So that is why I am able to add the contribution from each of these electric fields, and therefore this factor of 2. So I could write the strength of the electric field between the plates of the capacitor as being sigma over epsilon naught, which is therefore equal to Q over epsilon naught times A. Now we are going to ask, what is the drop in electric potential between the plates? So we will imagine that we begin at the positively charged plate, and then we walk down to the negatively charged plate. Overall, we have walked a distance of d, the distance between the plates itself. Because the electric field between the plates of the capacitor is uniform everywhere, I could write the change in electric potential as we move from the positively charged plate to the negatively charged plate is given by negative E times d. Now I am going to say that V is understood to be the drop in electric potential. So because I am saying V is the drop in electric potential, the negative sign will be implied. So I'm going to get rid of the negative sign because it is implied, and plugging this value in for the strength of the electric field between the plates, I could say the drop in electric potential between the plates is given as Q over epsilon naught A times D. I could then rearrange this equation to end up at our final result, that the charge on one of the plates is related to the voltage drop between the plates, given as epsilon naught A over D. We have demonstrated that the charge that accumulates on one of the plates of the capacitor is proportional to the voltage drop between the capacitor plates, and that constant of proportionality is epsilon naught A over D. I will assign this term, epsilon naught A over D, a new symbol. I will call it the capacitance of the capacitor, and I will assign it the symbol C. So then I could write Q is equal to C times V, where C is equal to epsilon naught A over D. Now, Q equals C times V is going to be one of the most important equations from this chapter. We will encounter it a lot. If we are working with a parallel plate capacitor, then the capacitance is described by epsilon naught A over D. But just as a heads up, there do exist capacitors of other shapes, and those other types of capacitors have their own equation that describe their capacitance. Now, one thing I want to say about capacitance is notice that the terms in the capacitance are purely geometrical. A is the surface area of my capacitor, and D is the distance between the plates. Those two quantities are under my control. I could go to a shop and build a capacitor of a given surface area and a given distance between the plates. Epsilon naught is a fundamental constant of nature, however. Nobody is allowed to change the value of epsilon naught.